Okay, welcome back. So limits part two. In the first video, we had discussed mainly three ways of solving or evaluating limits, and that being we would ask, can you plug in? So to recap, if you just have something very basic, limit as x approaches 2 for 3x plus 1, any normal looking function that does not have a fraction, you can just plug in and that's going to end up giving you a result. Obviously, that's not going to happen very often because that's pretty easy. The next thing we looked at was, does our limit factor? If you have something, obviously there's a lot of cases of things that factor, but just as a basic example, in this case, you cannot plug in the 3 because it would make this equal to 0 on the bottom, which means you would head to your next idea. Does this thing factor? If yes, we would factor it. You would cancel, and then you would plug into what's left. And in this case, that would give us 6. The third thing we looked at is there a visual component to this limit? Do they provide you with a graph, or is it a graph that you should maybe know? We looked at three graphs, that being absolute value of x over x, 1 over x, and 1 over x squared. We said that that graph looked something like that. This one looked like that. And the last one was that. So you could be provided a graph, or you could possibly be asked to know a graph in terms of evaluating limits. So that pretty much summarizes the first part of limits. This video will start with our fourth idea, and that being, could it be a trig limit? And the trig limits that you may or may not see, they're not very in depth. It really just boils down to a unit circle. So if I said something like the limit as x approaches 7 for sine of x pi over 6. Technically, this is just number one plugging in. I give it its own category. This is not an official list. This is just how I teach limits. I give trig its own category just because in order to solve this, you are plugging in, but we also have to know the answer to this. So you have to know the unit circle. So sine of 7 pi over 6 on the unit circle, hopefully -1/2 makes sense to you there. If it doesn't, you would want to rewatch the video on the unit circle. So I could give you a whole bunch of, fill in the blanks for trig stuff here, and it really just boils down to plugging in and knowing the unit circle. The fifth one we could come up with is we could rationalize. And rationalizing usually refers to something involving a radical. So let's take a look at what that might look like. If we said the limit as x approaches 0 for the square root of x plus 3 minus root 3 over x. Let's see how that would work out. So we look at this and say, could I plug in 0? And you cannot, because that would make the bottom equal to 0. And then this is obviously not something that factors. This is not a graph. This is not trig. If you have radicals, though, you can do something that's called rationalizing. And rationalizing means that you multiply the top and bottom by what's called the conjugate. And the conjugate is essentially the same exact thing that you had, but we change the middle symbol. Okay, so let's see what happens when we do that. So on the top, this is technically something that needs FOILed out, multiplied out. And on the bottom, we can just kind of smush these two ideas together. So on the top, if we were to FOIL this out, first times first, if you multiply a radical times the same radical, that's just going to leave you with what was underneath the radical. So side example, like if I tell you the square root of 2 times the square root of 2, that's really the square root of 4, which is 2. square root of 101 times the square root of 101, we don't necessarily know what that is, but it's going to result in 101. So the square root of anything times the same square root of anything just leaves you with the anything that was underneath. Okay, we're foiling, so we have to do the outer and the inner. And hopefully it makes sense to you to say that these are the same exact things, except one result is positive and one result is negative. So it would be plus root 3 times root x plus 3 and minus root 3 times root x plus 3. So the outer and the inner are going to cancel out. We don't need to write them. And then last times last is going to be minus 3 because a negative times a positive is a negative. On the bottom, we're just going to smush these together. So it's going to be x times x plus 3 plus root 3. Okay, what else do we see on the top here? 3 minus 3 is going to disappear, right? Because that's 0. So I'm doing this in markers, so I can't erase it, sorry. But that would vanish. Now remember, this is the limit as x approaches 0. And now since we are out of things on the top, these x's that are hanging outside, these also cancel. So now I've completely run out of things on the top. So this is now the limit as x approaches 0 for 1. If you run out of things on the top, it's just 1 over x plus 3 plus 3. Those are under radicals. Okay, now remember, it's the limit as x approaches 0, and you can always plug in from strategy number 1. You can always plug in unless it makes the bottom 0. Well, in this case down here, plugging in 0, while it makes this x 0, it does not make the whole result of this equal to 0. So if we let that be equal to 0, this is now going to be root 3 plus root 3, and that's 1 over root 3 plus root 3 is 2 root 3. And that is an acceptable answer. 1 over 2 root 3 could be your final answer to that. Now, could you re-rationalize that? Sure. But you've gotten to a whole solid answer, and that would be acceptable for that limit. So coming in at number 5, you could rationalize these limits. All right, and the 6th one, we could be looking at a situation where you need a common denominator. So what are we talking about when we're saying common denominators? Common denominators tie into when we're looking at a fraction. So example, the limit as x approaches 0 for 1 over x plus 5 minus 1 over 5, and all of that divided by x. Okay, so can I plug in 0? No, because that would make the bottom of this equal to 0. So we are going to look at setting up a common denominator. So the first thing I'm going to do is I'm going to, in my head or on paper, I'm going to think of this x as x over 1. That way it's a fraction too. And then we have a whole fraction divided by a whole fraction, and that'll kind of help clean things up in a bit. Okay, so we're going to forget about this for right now. But up at the top, if we wanted to combine those, we would need to use a common denominator. So 5 and x plus 5 are two totally different things. So for example, this one would need a 5, and this one would need an x plus 5. And whatever was missing is what you have to include on the top. So since this one was missing a 5, we're going to multiply the top by 5. And since this one was missing an x plus 5, we're going to multiply that top by x plus 5. We'll carry along the x over 1. Okay, now that you have a common denominator, you can subtract this quantity. But now you got to be careful in algebra when you subtract a quantity, you have to distribute this negative sign. So this is really minus x minus 5. So when we do that, this is going to be 5 minus x minus 5. And 5 minus 5 is going to cancel, but then that's going to leave us with negative x. So this is negative x over 5 x plus 5 divided by x over 1. Okay, and so the reason that I did this x over 1 to begin with is when you have a 4-story fraction, it's a very good shortcut to know Example, if I tell you A over B over C over D, to quickly combine these, the A and the D get multiplied and the B and the C get multiplied, and that becomes AD over BC. And we want to apply the same logic here. So this becomes 1 times negative x is negative x, and then this becomes 5x plus 5. So I just slid the x right in there. You could put it anywhere really, but it just makes the most sense to kind of keep it clean by putting it right there. Okay, does anything cancel here? Yes, this x and this x could cancel. And since we're out of things on the top, that leaves us a -1. So this is now the limit as x approaches 0 for -1 over 5 times x plus 5. Could I plug in my 0? You always want to keep one eye on the thing that you're approaching, and could I plug it in without making the bottom result in 0? And the answer here is yes, you could do that. If I put in 0 here, this becomes 0 plus 5, which is 5. 5 times 5 is 25, and then that would result in -1/25 for your final limit. Okay. So in terms of limit strategies, things to kind of summarize what we've been talking about so far, we always look first and say, could I plug in? If yes, great. If not, does this factor? If not, is this some kind of graph, or do I have a visual? Do I have something that I can look at to just come up with my answer? Does it involve trig? Does it involve radicals? If it's involving radicals, we're going to rationalize. Does it involve fractions? We're going to use a common denominator. And then in terms of this video, that's going to be kind of where we cut this off. There is a 7 and an 8. For number 7, this will be the third video I'm going to make on limits, and that is called the limit of a composite. That's its own story. That's kind of a mess that we'll use a separate video for. And the 8th one, we have to learn more calculus in order to do that. We don't discuss that till later in the year, but for the sake of making a full list of notes, that's called it's pronounced L'Hopital's rule. Number 8 is not in the first unit of calculus. We will get to that later in the year. But that is pretty much the full list of limit strategies for what we're looking for. So if you wish to look up other examples, you can plug in, you can factor, you can graph, you can trig, rationalize common denominator. In the third video, we'll be talking about composites. And then later in the year is L'Hopital's rule. So we're winding our way down to having an example here of all the different types of limit questions that you would need. So that's it for this video. Nice, short, and simple. I hope this is making sense, and I will see you guys in the next video.